in theory, everything is working. Okay. So anybody in the online section, feel free to ask questions when you have them. All right. What do you guys want to talk about? Talk to, obviously, all the good stuff.
Everything.
So, I mean, like, what do you guys think is the most challenging part? And first off, how far do you guys cover? Because I was a little.
The last chapter is the article.
Okay. I read other different things. Because I didn't do my other right here.
Yeah.
Okay, so, well, I mean, start asking me questions. I know this stuff. It's
Okay.
chapters. So if you have like a specific question out of the book you have to show people.
I think the something you want to know is the strategy for the input. This yeah, this strategy.
The strategy.
Yeah.
Okay. Oh, that's tall order. Okay, so if you're just given some interval, right? You're asking me, what should I do first? Like, what should you look for? Okay, well, if you have something rational, right? With a square root. Gives them true set. Yeah. So true set, right? Like this is plus or minus, right? If we've got something that's rational that's like not, right? That's probably too easy, right? Like a quadratic like that. What do you think?
Wasn't like the vector of the
Okay. What? Chain rule is not exactly where I'm going with this. You would want to use partial fractions. Sorry, I would get nervous when we spell something wrong on these boards, and then we'd be like forever immortalized or something. I don't know. So, I mean, like, these are just a couple examples, right? So, if we've got something, well, I can't really use a drawing, All right. So, if we've got something with like cosines and sines, right? Trig reduction. Yeah, that's using all those fun trig identities that you thought you could forget, but you can't. So let's see, that's a lot of them. So partial fractions, trig sub, trig reduction. What other ways we have? We have, if we've got something like f of x, g prime of x, right? Then we all know what this is going to be. Integration by parts, right? What other ways of integrating do we know? Are there other ways? More ideas? Yeah. Yeah. So we got something like f of u. I think that's it, right? You said integration by parts, trig sub, trig reduction. Part fraction? Kind of a tall order, right? But these are the kind of like warning signs you want to look for. If you see a function where it's obviously got other stuff inside of it, right? Then we're going to want to use u sub. If you see something with a big nasty square root at the bottom, it's probably going to be trig sub, right? Not 100% of the time, granted, but it's kind of a good starting point to think about, right? Cool. I mean, if you've got some written out, I do not want to make them up. They will come out to be the nastiest thing you've ever tried to integrate before. Promise you. if you find an example, I'm gonna get this time. Oh, no, it's fine. So, you guys all just wanna write your name and student ID number on anything? Yeah. Uh-huh.
Here.
Okay, so we're finding, you're gonna go to your first at. Okay. So. File. So, anybody, where shall we begin? Okay. Because the important thing to remember is that we've got that formula that I always mix up where the letters go. Does anybody know what formula I'm talking about?
One.
1 over prime.
Prime F inverse of A. Right?
I think so. That should give us what we're looking for, right? So this is our guiding light. Okay. That looks right. I'm always scared to admit it myself. Okay. So good. If we take this derivative, right, then we'll know what we're plugging into. So f prime of x is, what do we get?
Well,
Squared, right?
okay.
Good. All right. The other important thing is that we need the inverse at a particular point, right? So there are two ways to go about it. We can solve the whole inverse and do that whole thing and then just plug the letter in, or number in rather. Or we can set this whole thing equal to 7 and figure out what x had to be, right? Good. Already seems easier in that way in this case, right? So we know that f of x equals 7, so, well, yeah. So x equals 7, so x equals what?
0.
X equals 0. So that means that
Oh, let's choose A equals 7 for fx.
we're this.
In that case, it choose A equals 7, right?
Yeah.
But why fx?
Okay. So if we're looking for f inverse of a, right, that's going to give us some x value, right?
Oh, yes.
So this is interchangeable with having f of x equals a. Right? That's the
Oh,
right
yeah,
trick.
yeah.
Yeah. Awesome. So now we know what f inverse of a is, so we can plug that into our derivative, right? So what's f prime of 0? It'll be 7 as well, right? So our f inverse's derivative at 7 is 1 over 6. That kind of got way down there, so if you can't see it, let me know. Any questions on these are all experts, very knowledgeable, I'm sure. Everybody cool if I change the page? Okay. All right. Did you find some examples you want to walk through? Okay. Anybody else have questions in mind? Now is the time. I'm way too excited about this, so if I get annoying, let me know.
We need that.
I'm sure.
I have one question, and I feel like it's gonna be something that I'm gonna be like, oh, good stuff. But, so this rule, that's like derived from, not, just by the natural law.
Yeah.
And then, okay, when I was doing that, I was getting something slightly different, and it might have just been like an algebra mistake.
Okay, so we have some letter raised to the x, and we want to be able to take its derivative with respect to x, right? So basically, this would be a case where, anybody know how to do this, like how to show that this works? I mean, we know, right, that it's ln of c times c to the x, right? Why is that? Does anybody know the justification?
I thought it was because we changed the natural law before we said that equal to y, y equals to the x, and then the natural law of both sides.
Yeah.
I just did my math wrong or something.
Okay, yeah. So it's exactly like you said. Think of some y equal to c to the x, right? Then you would want to be able to take the natural log of both sides. So natural log of y is x natural log c. And then we would want to take the derivative of both sides with respect to x, right? So we will get y prime over y is equal to natural log c. So we would multiply by y, right? So y prime equals natural log c times y, which was justification.
I like used the chain rule for some reason, so it was like,
Yeah, because c is a constant, right? Yeah.
that's why
There we
I
go.
was pretending it was not.
That would make things significantly more
Yeah,
complicated.
that's why I was like, what is this? Thank you.
Alright, no problem. Any other questions on this? No other questions? Okay. Whoopee. It's the highlight of my day. Yeah.
It's this one.
So, we want to find the limit of x goes to 0 of p to the 5x minus 1 minus 5x over x squared. And it says to use L'Hopital's rule if appropriate. Okay. So, if we were to take this limit as it is, what do we get? We get 1 minus 1 minus 0 over 0, 0 over 0, right? So then we want to apply L'Hopital's because it is a fractional indeterminate form and we can do that, right? So what is the derivative of our top? Good. Derivative of the bottom, right? That x got a little low. There we go. So now if we were to take this limit, what would we get? 5 minus 5 over 0, which is 0 over 0. Drat. Well, let's try it one more time for good measure, right? So, this is also the same as what? What is this going to turn into? It's derivative of the top. Good. And the bottom will be, oh, that looks promising, right? Because now if we take this limit, we're going to get 25 over 2, which is not 0 over 0. So we're happy. Yeah? Yeah. Cool. Any other questions on that? We'll be solved, right? As long as you don't have a non-fractional form, then it's a jerk. Okay. So, new page. What do we got? Big sub is so cool. I think it's amazing what one little triangle can do for you.
Just wasn't. But same time.
I will be honest with you, the first time I saw trig sub, it was like the bane of my existence. It was not until after I'd taken my final and I had like this epiphany that I'm like, oh, I could have been doing this the whole time. Yeah.
So,
If you have an example, I will do it. Hey, wow.
You know, my magnifying glass.
Okay. Yeah. Leave that as a plus 2. That's 16. That is much better.
I didn't have that.
Okay, so that is a 16. I was like, wow, 10, that's kind of cruel. Okay. Awesome.
Basics.
Yes. So whenever I see trig sub, I always think about what the triangle would have to be first, right? So I know what the theta is going to be there. All right. If I have an x squared plus an a squared, I know that those both had to be legs, right? So x is 1, and then the square root of 16 is the other, right? And that's the only way that we can get x squared plus 16. That's weird. Yes. So you can use this to figure out what trig substitution to use every time.
I was just trying
This was my epiphany, guys! I kid you not! Is that the best thing? I did not figure this out until I walked out of my final for Calc 2. That was like the worst thing ever. I don't think a lot of them think about it. They've just done it 100 million times.
Yeah, they just do it.
So it's X, you take the square.
Yeah, so what is x going to be if we think about these trig functions, right? Yeah, so x equals 4 tangent of theta, right? Theta, man. Okay. So, equipped with that knowledge, we can change all this stuff, right? So we also need our dx before we get too far. So
Or
theta. Okay. So now that we've got all this, we plug everything in, right? So we will get 4 secant squared theta theta over 16 squared theta, and then we get the square root of, oh man, I didn't think that's very long enough. Okay, big square root here, right? So we will have 16 squared theta. Okay. I guess that wasn't so bad. All right. And from here, anybody care to give us the next step? Good call. All right. So, I'm trying to keep all my colors and stuff. This was like thinking bubble. Okay. So, we'll have all this stuff to stay. 16 times the 4 that we're going to pull out of the square root, right? There's 1 squared theta. Okay. So, see if we can multitask. What's tan squared plus 1? Squared. Right? Yeah, so I pulled the 16 out and made that a 4. Because if we take the square root of 16, yeah. And then I just moved it over by my other coefficient so that it didn't look like I had tangent of 4 theta. So, definitely clarify. I'm just trying to make sure it all fits on one board, because trig substitution can get rather lengthy. So, which is staying feminine in your handwriting, I swear. Okay, so now that we've got this, we can start doing a little bit of canceling all over the place, right? we can mix these fours. Probably do that with the color. Okay. We can mix these fours, right? And then this square root and this square. Yep. So then one secant, so this one, right? Okay, so let's see where that puts us before we get just scribble black the whole thing. So we've got secant theta d theta over 16 tan squared theta. All right, that is looking considerably better, right? Well, relatively better. All right, so what should we do next? Yeah, so this is where we want to pull out our u sub. So which one do we want, tan or secant? Okay, so if we've got tan, this is going to not work out as well, right?
No,
Okay, so this is not a good plan. Think again. Okay, so we're going to use this identity again.
Yeah, so would that just be like under?
you do it to sign.
Turn it to sine and cosine.
One.
Okay, I'm willing to try stuff. Let's just try stuff, right? Okay, so let's just change it all to sine and cosine. I'm going to pull that 1 out of over 16 all the way out. Okay. So then we can do a bit more slashing with our black one, right? So we can get rid of this cosine and one of these cosines, right? Okay. So I'm going to take this up here now. So that leaves us with, if we've just got 1 over this being reciprocal, right? So over 16 cosine theta over sine squared theta d theta, right? Okay. Now you substitute it. This is why these are so long. We have to do so much stuff. Okay? So we want to pick the square thing to be our u. So what's our du? Mm-hmm. Cosine theta d theta. So that means we have 1/16. Okay, so then we get du on top and u squared on the bottom, which is 1/16 u to the -2 du. So what is our integral? Plus c. So to write that a little bit nicer, right? -1 over 16 u plus c. But what was u? Okay, so -1 over 16 sine theta plus c. Oh, awesome. You are right. And I was just debating with myself where I should draw my next arrow to. This little corner under my thinking bubble. Okay. Over here. It's a math roller coaster now. Okay, we've moved the loop. So if we want to put this back in terms of x, right? Sine theta is what? Based on our triangle? Opposite over hypotenuse, right? So we'll get 4 over the square root of x squared plus 16. So, yeah, that?
Wait, where can you can simple for rectangle, right?
Oh, yeah, you're right. Not on the bottom. Bad ideas. Okay, let's just erase that right now. I got so excited about anything reducing in that. Okay, so we've got the 16, got the 4, got that square root. Good catch, guys. Brownie points to the front row. So, reciprocal, we've got the square root of x squared plus 16 over, this is negative 64, right? Oh, so terrible second. Any questions on this? This? Technically, yes, these are equivalent and they're both in terms of x, but compound fractions can be in trouble sometimes depending on how your professor's opinion is on that. He would have probably said something in class. If he just left his like this, chances are good you can leave yours like this, but I don't sit on your class. So I'm going to simplify them as far as I can. Was it okay if I clear the page? You can leave some writing?
Just go over like in general,
So-
what we did, like.
Yeah. So with trig sub, basically you want to identify first, right? We said there's this nasty square root in the bottom. I want to be able to do something about that. Think about your triangle. Figure out what x would have to be, right? And then find your dx, make your substitutions with thetas, right? Reduce it down, try and get it as far as you can that way. If need be, you have to do like either another trig identity or a u substitution, depending on how everything kind of plays out. And then you'll get it either in terms of theta and turn it back into x, or you'll have it in terms of u, which you turn into theta, which you turn into x. Unless, of course, it's a definite integral, and then you just get to plug numbers in, just straight.
So when you switch it back to that.
Yep, so the triangle is double handy.
So, in the exam, can we just draw?
I don't know why you couldn't draw It's not like you're cheating. You're just identifying what's in the problem, right? Yeah, so for all you guys who came in late and missed the really awesome thing about triangles here. Okay, is it okay if I make a new page just to talk about the triangles? Okay. So, as I was saying, this is something that I realized when I was walking out of my Calc 2 final, when I did this. So, like, let's say that we have a square root, right? So we've got x squared plus a squared. Well, if I think about what a triangle would be, and I think about Pythagorean theorem, right? If I have two squares added together, that means that they must have both been lengths of the original triangle, which makes my hypotenuse that square root of their sum, right? So then you have to think about, okay, what if I have x squared minus a squared, right? What does that mean? Well, that means that my x must have been a hypotenuse, because otherwise I wouldn't be doing that, right? Then you would make a one of your legs, and the other leg be that square root. Right?
So now the theta is.
Yep, and then theta is always this one. Great. And I mean, these ones can switch around, obviously. I can't remember which one this one to be which, but one has to be like, depends on which trig substitution you're going to make. So, and then the last case would be if we have a squared minus x squared. What do you guys think? What's my hypotenuse? Right? And then pick a leg, pick a leg. Triangles are the best thing ever.
So.
Yeah.
Oh. I see the trick.
Yeah. Okay. So everybody cool with this? And everybody who came late trying to get? Excellent, guys. All right. So what else you got for me? I'm gonna check if anybody in online questions ask questions here. Oh,
Can you see us or they can
They can see what I'm writing and they can hear whatever gets picked up by this little microphone here.
Hello.
So they all say hello. Anthony is in our online section today. Okay, so to answer your question, the 4 in the denominator of that last problem that I just cleared off and is on a previous page had to come from when we reversed the triangle with the trig sub. Did you figure that out later, or? He's typing. It takes a little while for him to respond. Oh, did I text him? No, I'm just on the chat. That's okay. All this tech is like, I get so terrified that I'm gonna like cut something off, or it's not just like you guys are all in the room. There's other people that I'm accountable for. Okay. Okay, so he's got substitution. Okay. So does somebody have another question that they want to talk about? Yeah. Okay, there's lots of questions. I will pull up that sheet again while he's, Okay, so there should be a way for me to go in my other pages. Those are my pages? Those are my pages. That's my math roller coaster. Okay. Okay, so he was asking how I decided to go from sine theta to this, right? And that comes back to this triangle. If I were to think about sine, that's opposite over hypotenuse. And the opposite is going to be the square root of 16, which is 4. And the hypotenuse is that square root again. So that's how I'm coming up with that resubstitution in terms of x. So does that fix your question, Anthony? Yes. Excellent. Then we will do more questions. Okay. Insert a blank page. Woohoo! Okay. So you have a question? Okay. Definite integral. Okay. All right. This is what we have. We have a definite integral. Is it a 61 or a 67?
That's
I guess it doesn't really matter, does it? All right. Well, we have a number. X squared over 9 plus x. Okay. So the question asked us whether this is convergent or divergent, right? So where shall we begin?
Well, let's first factor out the 67, so that's
Yeah. You don't really have to worry about this. It could easily be a 1, right?
And is this the actual like one of specific value, or can we get this? Like is it the x squared is 1, and then we can go 1 over x to the 4?
Yeah, all we have to ask is whether it's convergent or divergent, right? So what he's suggesting is that we can kind of make like a comparison. That this is like 1 over x to the 4th. Because when we get really big, right, for x, this 9 isn't going to matter. And then we're essentially looking at x squared over x to the 6th, which is like this, right? So if we're looking for just convergent or divergent, we can make this comparison and be able to tell.
And
Yeah.
What the pattern that I realized about 1 over x is that only 1 over x is the one that is supposed to specifically go with any other x.
You're exactly right. This power is p, right? And if p is greater than 1, then it's convergent. Oh, that's the wrong way.
Like twice as much area.
Other way.
The way it's
P is greater than 1.
the other variable
Implies.
is greater
if we have,
Well, I thought
Yeah.
it approaches.
it should approach zero.
Yeah, approach for-
Oh, right, I got it.
So if we have to show this is an example for limit.
Yeah. So
There you
if,
go.
yeah, so like this is kind of like your thought bubble of what you know you're gonna get to, right?
Yeah.
So if you wanna actually show your work, limit I choose R. Right? And you look really concerned with me for a second, I was like,
No, it's a-
okay, good to know. So from here, what shall we do? Not really gonna fix anything, right? Because we don't have any excellent fits.
Yeah, I mean,
Yeah. Okay.
Is
So
that reasonable?
that's what we were just kind of discussing very quietly here, because you have to remember that there's somebody trying to listen to this. Yeah. So the suggestions that we've been getting, right? We can ignore the 9, just like we kind of did here, and then like to
So all we have to do is write a limit before that, before the.
yeah. Well, and I mean, the technical thing that we're doing is we're saying that this is always less than or equal to the limit as r goes to infinity of negative r to r over x. That's the key part that we're missing, right? Because if it's going to converge, right, then whatever is below it will obviously converge as well. So as long as we can pick an upper bound that is easier, we can just integrate that, right? So then we would say, okay, the limit as r goes to infinity, we would do this integral, 1/5 x to the negative fifth, evaluated from negative r, or, yeah. So,
So 1 over x is the one that's divergent.
right, because when we integrate that, we get natural log, and
Got it.
it approaches infinity,
Right, yes.
right, and it's just,
Wait, that's what I got.
how big is the last thing?
oh, this is the third, by the way, and this is the 3, because I subtracted, so add it, just there.
Okay.
Okay, so I did this integral, right? This is x to the negative 4. So if I add 1 to that power, I get negative 3, and then this would be negative 1/3 out front. That got really, really sloppy, so I should probably just rewrite this last bit. Okay, so negative 1/3 x to the negative 3, negative r, right? And then if we were to actually plug this in and do the limit, we would get 0, right? Wait, would we? It's just kind of, oh god, what is that? Why do I have that? Go away. Okay, I bumped some kind of button. We're not going to bump that button again. So if we do this, negative 1/3, we would get x to the negative 3, or r to the negative 3. Yeah, that's fine. Yeah. Okay. Let's just do this. Because I'm gonna like debate with myself all night about this if we don't just do it. So humor me. So we got r to the negative 3 is still a limit as r goes to infinity, right? And then this is gonna be plus 1/3 negative r. Yeah, that's why it works. So then this one is gonna give us 0, and this one's going to give us, oh, no, because, yeah, so,
Divergent means there has to be an infinity somewhere.
Yeah.
Just remember in
So as
class
long
when you
as-
said we get a infinity and I said, you said screw it. Yeah.
number is good, infinity is bad, right? Number implies convergence, infinity implies divergence.
So 1 over x.
Yeah, because the antiderivative is natural log rather than another exponent, so that's why that one diverges.
So anything higher is that?
Yeah,
Yeah,
so
so that's
so
what
if
this,
it's,
this is,
if
that's what
the
this is about.
exponent is lower than x to the negative one, then it converges. If it's x to the negative one, it diverges.
Yeah. So this is the idea.
That's just,
So if P
you
is
can
greater
only
than,
use that if it's like, if it was a diverge or converge, really quick question, then yeah, other than that, it's not helpful if we actually have to do it.
What's the state? What's the state if the p equals to 1?
if it's equal to 1, it's going to be conditionally convergent, but that's not something you're talking about right now. That would be more applicable to series than integrals. So it's divergent.
But if the interval is
If P is less than or equal to 1, it diverges.
if the p was 1 and the interval is minus infinity to the infinity, but
Of
it's also
natural
divergent.
log, right? So the negative infinity is undefined, and so then it would diverge into zero. Because, like, if you think about what the graph of natural log looks like, right? We
Yeah.
can't approach negative infinity, right?
Yeah.
Yeah. So 1 over x could have that as a limitation, but the function would be undefined. Like over here, so then we would have undefined integral, which would be whatever.
If the x also are close to the infinity, 1 over x also is 0.
Right. So, like, what you're saying is p equals 1, right?
Yeah.
So we have the natural log of x evaluated from negative r, right? So this one, yeah, we'll get infinity for that first bit, and then we'll subtract undefined term. So it's infinity.
Where is the undefined one?
If we have negative anything inside a natural log, it's undefined, right?
Oh, yeah.
Yeah. So like even if we put 0 here, right? Then this is going to be going to negative infinity, and that's still like an indeterminate form. We would have to do sort of to figure out if it's conditional or different. Yeah. So that's what I'm talking about. But obviously that's quite a bit into this. So any questions on the easier couple that we started with rather than the natural log debate?
What about
Solving for
Oh, well, I'm saying, yeah, when I told him that, if it's x to the negative one, any lower exponent, you assume it diverges, right?
Yeah.
But when we have, that's only if it's, an approximation from like x squared plus 9x, we want to know whether it diverges or converges, where we can just knock stuff out and rewrite it.
Right.
And we can but we have to include the less than in our proof.
yeah, this is the key for knocking that stuff out. Is the
If we don't put
Finding
the
the
less
upper
than, then we're wrong, because that's an approximation.
Because the idea is that if we can find a convergent curve that is close to this or above this at all points, then we can use this as an approximation.
And so I'm saying that that's useful, but only when we have like 1 over x and a negative 4, 1 over x and negative 3. I have a reciprocation problem where we do diverges, and you actually have to find the derivative.
Oh, do you have an example? Is it okay if I clear this page?
Yes.
Okay.
I have,
You guys have good questions.
I have these. They're not ridiculous.
Alright, so do you have a particular favorite?
What?
Do you have a particular favorite?
Oh, that was just a recitation, and I was smart enough.
Oh, well, there you go.
No, that's
Okay. So we're just, all of these are
7.
about convergence, or there's just doing the integrals?
I don't.
I don't know what you call it.
Wait, do we have the football one? Is that one on there?
No, that was not good.
Yeah, but if we know how to do that football one, we can take on any.
If it's not gonna be on your test, we can come back to it at the end, but but we would have to answer all the other
Oh
questions.
my God.
Like when you're actually
Yes.
So, actual
I'm
questions.
missing a third. No, see, we're missing the middle. So, no, I'm missing one, so that's 66.
Oh,
I'm still
this
paying
one's
two.
just-
No,
Okay. Okay. So, if we have this, right? So if we
Take a picture of it. Oh my God.
want to do that,
You want to take a picture of them? Because the recitation problems are impossible for you. Solving the actual test, it'd be like, oh my God, they studied all of that for nothing.
okay. So if we have this, what is the antiderivative? Not tangent,
Inverse tangent.
inverse
Sorry.
tangent.
Sorry.
Oh, I'd rather have that with it. As r raised to infinity. Okay. Tangent inverse of x evaluated from negative r to r, right? Okay, so that means we have, kind of have, we can't really plug in infinities, right? But we're gonna kind of think of it that way, just for the sake of writing this somewhere. Okay, so here is where I would think about what the graph of tan inverse looks like, right?
Yes.
Like this. And these are asymptotes?
At I have 2 and then pi over 2.
Yes. Okay, so then we know that at infinity, we're going to get pi over 2 minus negative pi over 2, which gives us pi.
Yes. And that sounds good. The area of this pi was
So, when you do a problem like that, you basically getting anti-derivative.
Finding the asymptotes of that one.
Well, not necessarily.
Well,
Like
with an infinite one, it would have to be asymptotes from this. Because if they're not asymptotes, you're going to get infinite values, right? So if it's not an asymptote, it's divergent. Yes.
So, all those problems.
Yes. Or you would have to say divergent and then each step, right? Because usually the question will be evaluate the integral if it converges. If not, say divergent. Yeah. Yeah.
What trigonometric mental graphs would you recommend?
Trigonometric mental graph.
Well, see,
Oh,
like that. Like,
sorry, that was just a really great phrase. Yes.
It's because, see, off the top of your head, if you don't know what it looks like, you're sort of screwed. Like for the
Yeah.
1 over x squared, even though they're very similar, they're completely different. So I can understand when not knowing the graph there is, But for trigonometric functions like this one, if you didn't know the graph, sort of.
This is the only one that has nice infinite asymptotes. So,
Oh, okay.
But you did say fast and no sign and really well, because I didn't
So, okay, so
okay, so
It's not
sine
line.
and tangent.
I had a,
Then-
I'm sorry, I had a physics test that day, and that's all I was studying.
Yeah. Now I wrote it down. No influence for sure.
So tangent
You
and
guys know all about it. That's what I wrote down. Know all about
Oh,
sine
God.
inverse and tan inverse. So who wants, I just wanted to know the aspect.
no, it's not. It's not. Really.
Where's the asymptotes of
Sine inverse, I don't actually know what's the top of it. Right, because that's going to be,
It kind of,
well, because, okay, so if we're talking about sine inverse
but
of x, right? So, do you know what it looks like?
I think it's like
It's basically
like
like
this. But I'm not really trusting myself because when I
Okay.
did my notes.
Well, let's think about what you've got down, right? So pi over 2 gives you positive values, so that makes sense, right? So we want it to be 0 at 0, and we want at pi over 2, or at 1, it should be pi over 2, right? Or which way does it go? x is 1, right? This is pi over 2. Okay, so the bottom will be clearer, I promise. So at negative 1, this should be negative pi over 2, right?
But
And so then that's the sine inverse on
Oh,
its own,
really?
right?
So it's from,
Because if you go around more than that, that's not going to work, right? It's no longer a function. If we try to do more periods in this, because it would essentially just kind of like wiggle along the y-axis, just like it would along the x-axis, right? So,
but the domain.
and that makes sense, because that's the range of sine, right?
Yeah.
Yeah.
Inverse.
See what I mean? The problem comes in with the domain of x, right? If you're talking about that, was all the limits is all the way around the unit circle. But the range of sine inverse is only from negative pi to 2 to pi.
So for, and just how like it has bounded, it's pretty much like the same numbers as with these line on the x-axis.
Well, because tangent can be more than that, right? Because sine and cosine could be anywhere between negative 1 and 1. So you can make as big a fraction as you want. That's
Oh,
why.
that's why I can,
That's why when we look at the graph of tangent, right?
it can be different.
Yeah, it has asymptotes like this, because we can have infinite y values for tangent. And then it's like a piece, right? The idea with if you know the original trig function, you can just rotate them and get the inverse function, as long as you know where to constrict the domain you're in. Okay?
How the domain of the reverse of the sine is minus pi over
You mean the range?
2. The domain. Is there a domain of
Because the range is the y values and like the y-axis, right? And the domain is the
okay, the range, sorry.
Yeah, that's what we were discussing here. Like normally, sine can be any value along
Yeah.
the unit circle, right? But in order to only have a function rather than repeat, because technically, like this would have gone up
Yeah.
like this forever. But to make it a function, we have to restrict it to just this square, or it's no longer a function because we'll have multiple y values for every x.
So this
and
is
so
a
the one-to-one
general
rule.
rule for that, right?
Yes.
is it the 101 rule? Is that what that is?
Yeah. I think so. Yeah. Because we would want, yeah.
Alright.
Yeah. Okay. Okay, back to this page. We've had a really in-depth discussion about trig now. Okay. What else? We got about an hour left. So.
This one.
Okay. Oh, Jesus, that's me. I'm sorry.
Okay, sorry.
Is it part of the fraction?
Okay.
Is that what we're doing?
Keep reading. Right?
Yeah.
Okay, and we're just supposed to integrate this, right? This is the plus sign, by the way. It kind of got mutated. We're just integrating this. So what should we do?
Oh, I just like getting rid of constants.
Okay, if
Because
we can pull a 4 to the outside,
it's,
sure.
it's like one of those traumatizing things, you know, it happened once and you're traumatized forever.
Okay, I can understand that.
So can we just take the natural or just yes, then do it with it? So yeah, that's just
So,
X.
you can't do that. You can't have an integral inside of a natural arc, whatever shenanigans that just sounded like to me.
Yeah, you.
Okay, and this was the question, right? I copied that down.
Yeah.
I don't.
There's like it's 6 people that
It's all-
don't corroborate this.
Yeah, it's not.
It's the new, so this is the new guy, yeah.
Oh. This is the website. define the homework,
Uh-huh.
but I don't know how to.
Okay, but is this kind of question on your test?
I don't know.
Wait, what section?
So like if this isn't going to be on the test, then we can assess this in the arc another day.
Or 7.1.
Okay.
Yeah, that would be.
Okay. Well then,
Yeah.
so the only other thing. Right. Whether that's helpful or not, it's just a new perspective. Because we can't use a u substitution because we don't have another e to the x. We can't use partials because it's not linear or quadratic or
Are we
polynomial.
supposed to just find the integral? I think that was a really good
So just find the integral. There's no limits of integration. So
Just
Oh,
no,
you can't.
yeah.
It's
Okay.
not the x power, it's because it varies, so if we have one, yeah,
Okay.
Yeah, like this.
So what's du?
x to the n to the
Okay. So what's dx?
one.
Right.
Right.
And what's e to the x? Oh, it's minus. It'd be creating, which is something mathematicians are not usually known for. Although, if you look at all those proofs that we have, some of those are pretty creative. Okay. So now that we have,
Should we get into Taylor series? Taylor series makes up 90% of that.
I don't know why.
Okay, it's like a proof. It's a really nice way to prove. Really nice.
okay. Anyway, so now we want to try and rewrite this, right? We've got 1 over u, and then this will be times our du over u minus 4, right? So now what should we do? He's just lovely. Bless you.
Multiply it and use 1 over u squared minus 4u.
We have to have a derivative on the top, right? So natural log is a no-go. So since you have the solution open, I will let you tell your classmates what to do. Do you think you understand it?
Only.
Is there a substitution of integration like that? No. Is there a substitution of like minus?
Yeah. Yeah, we'll put the Oh yeah, okay, so, or, actually, so, this is equal to, so this is a side, right? Okay. So if we have 2 linear terms in the denominator, partial fractions. So a over u plus b over u minus 4, right? So then we get a u minus 4, a plus b u equals 1. Right? that means B equals 1/4.
So what you do is you put in 0 for u, and you let the -4 is equal to 1/4. Okay.
So there are lots of different ways you can look at it. The cover-up method, which you just described, you would pick u equals 0, right, which would eliminate the b term, and then we would just figure out what a would have to be, right? Or vice versa, if we say that u is equal to 4, we would figure out what a had, or what b had to be. Or the way I do it is to think about like a linear system. So I know that negative 4a has to equal 1, and I know that a plus b has to equal 0. So it's easy enough to solve for a, negative 1/4, and then b has to be the opposite of a. So that's 1. Because I know that if I were to make a common denominator, which is what we had, the top has to match, right?
Okay.
So a times the bottom of this one and b times the bottom of this one would have to equal 1. That's what we had on top. So then you can say, okay, I know that I had no u terms, right? So u has to equal, or the coefficient in front of u has to equal the coefficients in front of u on the other side. If you don't learn that way, it gets to be a bear, but that's how I learned it.
Can I plug in, for example, some legal stuff? Can I use already a set term and I can plug something into it, right? Because what I did is, in my head, what I did is I put u equals 0 to cancel the a equals b.
Right.
Can I do that?
Well, I mean, that's called the cover-up method.
Oh.
Yeah.
Oh.
It's one way to do it. Obviously, like, you can't say that u is strictly equal to this. But in the case that u is equal to 0,
And-
what did we have left?
Okay.
So that's basically what you're saying yourself, right?
Well, no, but now I, yes.
If your brain always used proper mathematical notation, that's what it'd be saying. Okay, we all know that we have that going on inside our heads, right? Just agree. It's okay. Okay, so then we still have this integral, right? So negative 1/4 over u plus 1/4 over u minus 4 u. And now each of those is a natural log, right? This was me making my common denominator, right? So like multiplying each of those and then just distributing. Like I said, my method is not your method. If you found a method that works for you, great. This was just another method that you could use if it helps. Okay. Cool. So now that we have our slightly more friendly integral, what are we going to get? Let's see, right? Or it won't be squared, right? No. Yes. Okay. So now we want to get all this distributed too, right? So we'll actually have
No, that's
the natural log
u
of
minus 4 minus u. Yeah, there we go. So it's not you. I would. So in this case, it'd be better to distribute first and then rewrite, right?
Yeah. So now that we've got this going for us, we want to make sure we get this back in terms of x,
Right.
because we kind of forgot what we were doing here. And then, so u was that. So we've got the natural log of 1 minus 4 over 4 plus e to the x plus c. No, because we have an additive term.
Oh, okay, gotcha.
It's good to have somebody to keep me on my toes. Mutual then. Okay, so I'm going to check for online questions. any questions on this page?
That was-
Yes, that was a partial fraction of the passage.
That's because of its function.
Yes. So we had a polynomial term in the denominator that happened to be a linear term times a linear term. So that's the decomposition. Do you guys need a review on the different kinds of linear or of partial fraction decomposition? Like, I mean, there's the irreducible quadratic terms and like you guys
Oh,
always
so
talk about
like-
linear.
Like ax, like a squared
Yeah.
plus b.
Yeah.
Maybe when we're going to start with something that's really complicated and then we have to do the division of units, we just do that
Yeah,
just
a
a bit
reduced.
more.
Yeah. Okay. Do you have an example like that or?
I think the one he did was 2x third plus x squared minus 100
Plus
over
2x to the third.
plus x squared
I should try to make sure that this is legible.
minus 100 divided by x minus 2.
Okay.
Oh, that's what.
Yeah.
So it's plus
I would.
it doesn't really matter.
It
You
doesn't.
trust
I don't
I
care.
tested.
I just didn't know if it was
Does it?
Well, it matters by like a simple factor of -1.
Yeah,
so
it's-
with a fraction.
I'm not gonna make a huge difference. So, okay, so this is an improper, right, improper rational function. So we would have to do the long division. Squared minus 100. And I know that this is the case where you can do synthetic division, but I don't remember how to do synthetic division ever.
Really? It's like a really
I don't know. That's what I was gonna.
Okay, well, if somebody can refresh my memory on how to do synthetic, that'd be cool. But because I know it has to do with like remainders
What's
and
the you need to cancel the x third?
The minus, I don't know how to work it with the x is -2, but I know if it's,
well, it's like the whole point is that you have a term here.
so x minus, yeah, with, is it -2, just -2, 2, 1, -100, bring this term down automatically, and then you multiply, 2 times -4 is -4, and this is -3, -3 times 6, and +6.
Well, let's find out. Okay.
I-
So,
We'll take my word on it.
all right, we're gonna go with long division. Yeah. So in order to do this first term, right, we want to make sure that we get whatever it takes to make x squared or x be 2x cubed. So we'll multiply by 2x squared. So we get 2x cubed minus 4x squared, right? So if we have minus this, so these will cancel, and then we'll get x squared minus negative 4x squared, so that'll be positive 5x squared minus 100.
Why not?
Well, that up to x. Oh, yeah. That should be 0x.
I mean, yeah, there's a plus 0x. It will matter in this term, I
It
guess.
doesn't matter.
Technically, yes. It's mathematical logic. Oh, God. Smart boy, yeah. Oh, yeah. Okay. Now that we're back, I'll check it. So, yes, technically there's a plus a 0x term here, which will come in handy when we talk about this next step. But I wasn't going to worry about it just yet.
Yeah.
You don't
Alright.
have to worry about it up until because you'll just go to you get to there.
Yeah, so now the point is that we want to match the 5x squared, right? So we add the 5x. But so that's why it's going to make a difference, because we'll have an x term here that we wouldn't have anything to subtract from. Which, I mean, if you subtract from nothing, it's just better to have a placeholder, I guess. So minus 5x squared minus 10x. So we'll get a positive 10x minus 100. Okay, so then the final term is 10. So we'll minus 10x minus 20. Okay. Well, I mean, it's minus minus, right? It'll be plus. I just try and keep my notation clear. So we should get negative E, right? And basic arithmetic, you know. Okay, that's an 8. All right, and so then that's going to be our remainder. So that means we've got this whole thing, right? 2x squared plus 5x plus 10, and then minus an extra 80 over our original term. Yes? Okay. Really, my enthusiasm is waning, and I don't know whether it's a good thing or a bad thing. Okay. So now we integrate term by term. So the first one, polynomial stuff, not so bad, right? So we'll get 2/3 x cubed plus 5 over 2 x squared plus 10x. And then the last one is going to be a natural log, right? So whatever he did was wrong, too, by the way. If you were paying attention to what he did with some information. That was no good. So, yeah. Because that's supposed to, the idea is that the end is supposed to give you the remainder that you're supposed to get, and like each one's supposed to give you the coefficient, and that did not work the way he was doing it. I can never remember how it works. If you Google search it later, it should be a quick study, but I always just go with what I know and do long division. Because everybody loves long division. Everyone. Okay. Everybody clear on the screen? Cool. Cool. All right. What else? I know. Calc is kind of amazing though. I think that's what makes it hard. There's just so much in Calc 2 you have to learn, and you guys are even halfway done. I don't mean to sound discouraging, but
Yeah, my friend does general calculus in the hobby.
it's considered like one of the most difficult classes anywhere, anytime, no matter what you do. It's okay, but see, once you get past this, you're like, well, it's all downhill from here. Yeah.
Please, thank you.
Yeah. You guys have a good night. So, other questions? Because we still have 45 minutes.
I'm taking mine.
I am not going to take your exam. That is unethical. See, now I have that on recording and everything. So, yeah.
I don't know.
Okay. Do you have any questions? You just said 5 minute version of the whole time. Okay. What you do? I'm just checking, making sure. Pulling you out of your comfort zone.
Can you do another one? And I have an example of it, just like one more.
Of the improper one?
Yeah, the two
Oh yeah, so that was kind of your
Yeah.
reason to look at it, so that one's good. Okay. Okay,
So I
so
have it, it's easier if you do it.
x cubed plus x squared plus 5x plus 16 over x cubed plus 4x dx. Okay. So, because this is the total degree on the top is equal to the degree on the bottom, we're going to have to do long division again. So, got x cubed plus 4x, and we've got x cubed plus x squared plus 5x plus 16. Okay, so what should we multiply by? 1. It seems kind of trivial, but okay. So we got x cubed plus no x squared, right? Plus 4 x's plus no 1's. Subtract that whole thing. So we'll get just x squared plus x plus 16. Right? Okay, so that makes our integral be 1 plus x squared plus x plus 16 all over x cubed plus 4x dx. Okay, having fun now. All right, we want to look at our denominator now because, well, actually, first thing you want to try is see if this is the derivative of this. If it is, then you just have natural log and you're done, right? Unfortunately, we are not that lucky tonight. So, yep, if the numerator is the derivative of the denominator, you say natural log, and you're good. Mm-hmm. Yeah. Natural logs are easy, in my opinion. They are not easy for everyone. But. Okay, so since we do not have that case, we're going to have to start looking at how to factor out the bottom, if at all possible, right? So how could we factor the bottom? Okay, so we've got x squared plus 4, and the top stays the same. Okay. Is there anything else we can do to factor the bottom? No. So this means that we're going to have one of those irreducible quadratic forms when we do this partial fraction decomposition, right? So we do another side thought. We've got a over x, and then does anyone remember how to do the numerator if we have an irreducible quadratic? Dx plus c, perfect. Okay. So then, depending on how you like to do yours, obviously you're going to have a different setup for this. I'm going to do the thing again. So I'll go through it slower this time though, so you guys can learn a different method in case you want to know more things. Okay, so we want to multiply a by the denominator of the other fraction. So we'll get ax squared plus 4a. And then we want to multiply this x times the numerator of the other fraction, right? So we'll get plus bx squared and then plus cx. And as before, we want this to equal the numerator of the other fraction, or of our original fraction, right? So x squared plus x plus 16. Okay. Yes, these two things will be equal. So now we can just look at coefficients, right? So first we think about the x squareds. So we know that here we've got a plus b, right? And in our top of the original thing that we're breaking up, we had a 1, right? So we know a plus b must equal 1. Yeah. So if we look at our x terms, what do we got? What over here has an x on it? Okay. And that should be equal to what? 1. And if we think about our 1 spot, and that should be equal to, okay. So this one tells us that a equals 4. This one, obviously, c is just 1. So if we know that a is 4, we've got 4 plus b equals 1. So b equals, good. Now that we know all this, we can redo our integral, right? So 1 plus a, which goes to 4 over x, plus, now we do our b, negative 3x plus 1 over x squared plus 4 dx. Okay. So now, integrate term by term, right? I'm going to kind of box our long division. Okay. Everybody take a deep breath, get ready. Alright, so we'll get x, right, plus 4 natural log of x, and then this one. This one is where things get a little bit trickier, right? So let's just leave that for now. So we'll do 3x plus 1 over x squared plus 4. Okay. So what can we do about that last integrator? radical though, so we don't want to do trig sub. Maybe. Okay. Well, let's kind of think about it, right? If we picked u, it would have to be the x squared plus 4, right? That would make our du what? Okay. So, is there a way that we could get this to work? Based on what we have in there. Because now our integral, like our hypothetical integral, looks like this, right? Just plugging in what we can right away. Is there any way that that's going to cancel that? No. You get that one. Go. Okay. Well, I mean, if you explain it to us, then you're going to learn it too.
Okay.
So, explain it.
So we split it up since we have the negative 3x plus 1 numerator, we have that integral negative 3x over x squared plus 4, and then equals 1 over x squared plus 4.
So, for right now, I'm going to get rid of this so that I have room to write linearly. Okay. So, taking this, you're saying we'll leave all that first bit the same, right? And then plus, we'll split this into two more integrals, 3x over x squared plus 4, and then 1 over x squared plus 4. That's each of those, right? So like we said, this one will work out okay-ish with the u substitution, right? So what did I give us? Right? Right, and now how about this one? It looks kind of like, we said about the trig stuff, right? But it's no radical, so what inverse trig function doesn't have a radical in sine does have a radical. Inverse tangent, right? But inverse tangent usually has a 1 here. So what can we do to alter that? Okay. So, I'm running all out of space. So I'm going to use a different color and just wedge it in somewhere. Okay, so this is kind of what we're thinking about, right? Tan inverse of x usually gives us 1 over x squared plus 1, right? So what if we had something else other than just x in here? What could we put that would give us a different derivative here? I mean, we could do trig sub. It's not going to hurt anything. Would you guys rather do it that way than doing it this way? This is kind of messy. Okay. We'll do a trig sub. That's fine. Okay. So back to blue. Think of our triangle, right? So if we have a sum, we know that the square root of x squared plus 4 is over here. And then we've got an x and a 2, right? And that's our theta. So what would we substitute x squared? Well, what's x, right? Yeah. getting this inverse tangent thing that I was trying to maneuver you to, right? Because if we say tan inverse of x over 2, it's gonna, yeah. So, anyway, so, just kind of forget I said that. So then the dx, right, is going to be 2 secant squared theta. Oh, that is just wedged right in there. So we have integral of 1 over 4 tan theta squared plus 4 and 2 secant squared theta d theta, right? Can I leave this up? No. Oh, Jesus.
You can.
Nope. That went away. We're good. Alright. I'll go again. What shall we do from here? More trig sub practice. How was your thing? Okay. Okay. Yeah, the sequence part. Okay. Yeah. So these cancel. Right? So we get the integral from 1/2 theta, which equals 1/2 theta, right? But we have to put that back in terms of x.
That's why you were.
No.
That's why I was trying to.
That's earlier.
Yep.
See, and I had that as the answer, but I didn't. All I showed was x equals 2. I don't know. I think I just like missed whatever we did.
Yeah. Okay. So we want to convert this back, right? What can we do? Well, we know that theta, right, is going to be the tan inverse of x over 2. So that's where we get this. Plus 1/2 tan inverse of x over 2. And then that's with this, all this other stuff that we had before. So x plus 4 natural log x plus -3/2 natural log of x squared plus 4. Woo! Ugh. Okay. That was a blast and a half, guys. Let's have more fun like that, please. this one question should be your whole exam. Look at that, you used like everything.
He said he's going to make it so that we finish it. So that
I'm expecting so much more. It's like a final. I'm expecting so much more.
last year or last.
Oh, okay. So the reason we couldn't just get the natural log to work with a substitution was because it wasn't going to cancel everything out properly, which is why we had to do the extra tan inverse step. Does that all make sense now that you saw the rest of it work through, Anthony? Just like talking to no one right now. It's really weird. But I don't want to type it up. All right, awesome. And we will keep going. So like, it's going to take me like, yeah. Sorry. I just thought that I saw something pop up and I thought it was going to ask me a question. So everybody's got the next one they want to do ready. There's like a question that you went through in class or one that you went through on your homework and you're like, I have no idea. I just copied Billy Bob, so you have it down. And what was like, sucks. These things happen. I went to the ARC and the tutor talked really fast and I just nodded a lot. No, I've definitely seen that happen. I caught him out of it, so I'm like, so it's fine, right? Yeah. I'm definitely that kind of tutor. Okay, yeah, so the answer,
Oh, it goes down.
yeah, and then there's the plus C that I would have forgotten, I got this whole thing wrong.
Because the 1/2 theta.
Because the 1/2 theta is we had to figure out what theta is, right? And that's what we talked about before.
Which is,
If we solve this thing for theta instead, we do x over 2 tan inverse. and
oh,
we
so
get
it's
theta.
so it's whatever.
So that's what it's tan inverse. Freaking sweat for real again. Got all over the place. I started writing like super duper small as we went. I remember the thing. Okay, awesome. So we still have almost half an hour. What do we got? Alright, so school have I cleared this page now? Okay, awesome. So, let's see, is there any kind of integration we haven't talked about trig reduction yet. Are you guys okay with trig reduction? Do you want to do some of those?
That's like
Yeah, so like you would have like
Wow.
secant to the fourth, then like tangent to the third, or whatever, what do you do? So that you guys are okay with? Alright, so that was the only type of integration we haven't had to do just by working examples. So, fun, I guess. I guess we haven't done integration by parts yet either. So, is there anything you guys are doing with integration by parts? Okay. So like, if you guys want to do some, I know at least 2 integration by parts questions that won't explode forward. You guys want to try some?
Yeah.
Okay. So, let's try. Alright, so I already told you it's integration by parts, right? So what do we want to make u and what do we want to make v? Okay? What made you pick x squared? Well, and you were right the first time too. If we take the derivative of u dx, it's still u dx, so that's never going to drop off, right? So, now we can plan. So we'll do our du is 2x dx, right? And our dv has to be the rest of the equation. So v is dx. Okay. So what does our integral look like now? Okay. You know. Okay. So that's x squared e to the x minus 2 x e to the x. Oh no. Research way too big. Okay. dx. Okay. What should we do about that integral? What is the integral of x e to the x? Well, we can't do u substitution, right? Because either there's no second e to the x, or there's no, you won't get one. So if I was doing a trig anything, that leaves us with just partial fractions, which there's no fraction, or integration by parts again. So yeah, in this case, I was tricky. I made you guys do it twice, right? So what do we want to pick for our things? And then has to be the rest of it, which makes this again, right? Okay, so with this in mind, we'll get x squared e to the x carried down from last time minus 2. Okay, so when we set up our integration by parts, this time what are we going to get? Good. Okay, and what is that last integral? Okay, so we're also going to distribute this 2 through here, right? So plus 2 e to the x. Yes.
Yeah, we just do that.
Alright, new page. So you have the example.
I just, what I did, we just do that, the conflict and discussion right there. Yeah. So that like sine squared x plus squared x. Sine squared x plus sine squared x. Actually, I just saw it before, and I said how it was just.
Oh, with a sign before the
So
stuff.
it doesn't make it that big of a difference.
Yeah, I guess we still go one step higher.
Complicated.
Okay, that is now to the 4th. Okay, so where shall we begin? They're both even. What do we do? Well, okay. First off, let's just kind of do a side note of trig identities. Okay, so what are some good ones? Like, we know sine squared plus cosine, well, I should have actually cosine squared equals 1, right? And then all the variations of that, you know, tangents and secants and whatever, right? What are some other good ones? Well, I mean, that's just rearranging this one, right? Still the same thing, essentially. Yes. Yes, you can. Because, like, if you were to divide through by cosine squared, right, you would have another one. If you divide through by sine squared, you would have another one. If you rearrange it, you get other ones. So I'm thinking, like, something to the effect of cosine, right? Do you guys remember the ones for cosine of 2 theta? Yeah, that sounds right. And actually, like, a combination of these first two can give you that, right? If you try really hard. Okay, so these are some good ones to think about, right? I mean, there's like the half angles and all that other stuff, but those are gonna be the primary ones that we're gonna use for these kind of problems, right? So, any of those catch your fancy if you look at this problem? Okay, you like the first one. Why do you like the first one? Okay, so if we use the identity in there, we'll have something with signs, right? But we can't do a U substitution because there's nothing to BRDU, right? So while that seems tempting at first, we can't actually get anywhere with that other than just making one expression with just signs or just cosines, whichever one you choose to substitute. So we don't like the first one this time, right? Okay, so if we think about this one, well, there's no signs anywhere, so that could be good, but that's basically going to give us the same kind of problem that we had before, right? We'll have all our stuff and all our eggs in one basket and know where to go with it, right? So does this one help us, or are we just starting from scratch? You know? We do have sines times cosines, so possibly if we could get this reduced down to things that don't have powers, that could be better, right? So let's give that a shot. So if we think about this as being sine theta, or well, these are x's, right? Sine x cosine x squared, and then an extra sine square, okay? Then this is almost sine 2 theta, right? It's sine 2 theta over 2 squared x dx. Okay, now, what else can we do? We could distribute this through, take out a 1/4, right? Sine squared 2x sine squared x dx. Okay, I just thought of some more identities that we want. I'm thinking of the ones that have like 1/2. Do you guys remember these ones? You have a little. Okay. You can tell me if I mess up my negative sign or not. Anybody else? Remember them? Okay. So this one should be 1 plus cosine 2 theta, right? Or, well, these are x's now. I have x's. I gotta stop changing it. And this one is just minus x. Okay, well, at least they look like the same variable now. They're like half a theta with an extra. Oh. Yeah. So, if we incorporate that, right, we can substitute out this normal sign. Do you guys see where I'm going with this? Can you know it? Okay. Because the point, well, okay, let's kind of come at this. If we just look at this, we don't have a cosine with a 2x or a cosine with an x, right? So we got to change something. Changing the sign 2x into something with cosine in it is just going to put us back where we were. So then we have to kind of think about, okay, is there a way that I can rewrite sine squared with something that's got cosine in it, right? And it just so happens I can, and in fact that something has a 2x inside, so that's even better, right? Because then that means I might be able to do a U substitution in the not so distant future. So, writing we could rewrite this sine squared 2x, and then x we plot another 1/2, right, and make this 1/8. 1 minus cosine 2x. Yes. Alright. Some promise here. Right? Because this is 1/8. And we're just going to distribute that through. So we'll have sine squared 2x minus sine squared 2x cosine 2x. Yes. It's a good thing I picked different colors because I know this stuff. Okay. So from here, the second part looks good, right? Because we've got something that we can do a u substitution with. Yeah? Now the first part, what can we do? We have a power on something that we don't have a u substitution for. Now we have to ask ourselves, is there another trig identity that we can use? So is there something that turns sine squared into something without power? Yeah, we're going to use the last one again, only this time we'll have a 2x in here to start, which means we'll have a 4x on the second part, right? So, okay, hold on to your hats, guys. So this is going to be the integral 1 half 1 minus cosine of 4x dx minus the 1/8 comes down again, just so I don't lose it. And then this one, we're going to use a u substitution, right? So u equals sine squared, or well, sine of 2x. So du is 2 cosine 2x dx, right? So we would get 1 half u squared du. So that's 2 separate ones. So like,
What happened to the?
yeah. So like this part goes with this part, and then this
You
whole
haven't
thing
worried about
is
it.
this whole thing,
Okay.
right? So I just split the one integral into two integrals because I knew that one of them I'm going to have to use substitution, one of them I had to use a trig sub. Right? Okay. And I just made sure that the 1/8 is in front of both of them so that I don't lose that. All right. So first integral, what am I going to get? 1/16. If I integrate, yeah. And then if I integrate cosine, so what's the integral of cosine? Okay, so if we have a negative cosine, then that's just a positive sign, right? So we got a plus. So I've got this 4x on the inside. We have to compensate for the 4 that would have been there when we did the derivative, right? So we get 1/4 sine 4x. Okay, and then minus. Now we're going to have 1/16 again, right? If we integrate u squared, what do we get? Okay. C. And then we would just put that last bit back in terms of x, right? Okay, so we get 1/16 overall. So x plus 1/4 sine 4x minus 1/3. And then our u was the sine of 2x. So we've got sine q 2x plus. When I look over this screen, it looks like I made a mistake in word and spelled something because I have like red underline. Okay. Any more questions on this? That was a good trig reduction problem. I use like everything. We have 5 minutes. It's one time review question or a bunch of concept questions. back to what all our trig identities are. This time we have an even power and an odd power, which makes our lives significantly easier. Because the first one we always think of equals 1, right? So which one do we want to sub out? Sines or cosines? Why sines? But then we'll have all cosines, right? So then that's not going to work as well, right? So we want to try and maybe do cosine. So this is the same as saying that I have cosine squared, and then one more cosine, right? So if I'm kind of planning ahead, thinking like chess, or just like a mathematician, we've decided that we would have to substitute sine if it's going to work, right? Which is good because now we have our du that we're looking for. So now it's just a matter of getting this term in terms of sines, right? So that's where the trig identity is going to come in. So what is this going to be? Dx, okay? So now it's a matter of choice. Do you want to distribute everything now and then get used, or get used now and then write less when you distribute everything? So I'm going to write less. So we want to make our u sine as discussed. So then du is cosine as discussed, which means we have u squared 1 minus u squared squared du, right? Take a breath, because I just talked really fast there. Alright, so now if we do some of our distributing, right? Or well, let's do the FOIL. So we've got 1 minus 2u squared plus u to the 4th du, right? Okay. So then that's the same as u squared minus 2u to the 4th plus u to the 6th u, which is 1/3 u minus 2 over 5 u to the 5th plus 1/7 c. Put in terms of x, 1/3 sine cube x minus 2/5 sine 5th x plus 1/7 sine to the 7th x plus c. Awesome. Any questions on that one? Much kinder trig reduction problem. All right. Any other questions that you guys want to ask before you take off here? Got it. You guys are doing great. By the way, I know it's hard. It'll be okay. Any last minute questions from the Adobe Connect section? Okay, for the last problem. Which problem was that, Anthony? Oh, okay, yeah, I remember that one. So, hang on. Going back to, where is that one? This one. Okay. So he was asking how we got this natural log one here. So if we can find where we did that. That was from here. right? And so there we said u equals x squared plus 4. So then du is 2x dx. So if we just have du over 2, that's x dx. So that makes our integral negative 3 du over 2 over u, which is how we get the natural log term. Does that make more sense? He may have left. Where is he still? So I hope that helped. I don't know if you walked away, Anthony. Oh, okay, he's there. That's so difficult. I can tell if you guys say stuff. Well, probably tell if you say stuff. Okay. Well, I'll pull it back up and I'll talk you through it. I'll just wish everyone else a good night here quick. So, all right, you guys are doing great. That was awesome. I love doing comp too, if you couldn't tell. So if you are still struggling and you want to come talk to me in the ARC sometime, I will be stoked to see you. I can't say that for every other tutor in the ARC, but I will be stoked to see you. So, you guys have a good one. And good luck on your exam. Okay, so I'm gonna start a new page and we'll just go through that one integral.
Yeah,
So we have negative 3x
I think we're just gonna go
over x squared plus 4 dx. So we say that u is equal to x squared plus
Yeah.
4, and that makes du 2x
Yeah.
dx. Everything's pretty straightforward right here, right? So then we can kind of say, okay, so now I know that dx is going to be du over 2x. And we can make like a hybrid integral and kind of assess where we are. So just plugging in what we have there, we can get this. But then we can see that the x's are going to cancel here, which leaves us with negative 3 over 2, 1 over u du, which is how we're getting negative 3 halves natural log u, which is going to be negative 3 halves natural log x squared plus 4. I know, I kind of brushed through that kind of quickly. You should have. It was amazing, you said?
Yeah, and I'll be see you.
Awesome. You remind me so much of someone I went to undergrad with. Like, it's unreal. I'm sorry if I was like being creepy about you. It was just like Aaron.
Thank you.
Have a good night, guys. Good luck. All right. So Anthony, does that clear everything up? Yes, exactly. Because before, I'm going to switch back to that notebook. Yeah, so before we had negative 3x plus 1, and so that plus 1 was screwing us up because we couldn't cancel anything to do with that 1 and make it all work out. We would still have that 1 over the x, which is why we had to change it into another integral and deal with the inverse tangent trig substitution wonderful mess thing. Okay? Yeah. Yeah, exactly. Yeah, because if we try to do the 2x thing here, there's no x here for it to work with. So that's why we had to decide to make it the two integrals. Yeah, exactly. So the same thing applies here. If we try to do 2x, that just doesn't work. Yep. All right. Okay. Any other questions? Okay. Good luck on your exam. You have a good night.